Let me introduce Professor Zhenan Bao. Professor Zhenan Bao is a KK Lee, Professor of Chemical Engineering, and Professor of Chemistry and Professor of Material Science and Engineering at Stanford University. Then Professor Bao founded the Stanford Wearable Electronics Initiative in the 2016 and served as a faculty director. And Professor Bao has published over 700 papers and over 100 US patents with the Google Scholar H index over 190. And also Professor Bao received a number of the awards. And okay, so let's please welcome the Professor Bao.
Thanks, Professor Kim, for the introduction and for invitation to speak here. And so today I'm going to tell you about skin-inspired organic electronics. The plan for the talk is to start with motivation and the overview on what we are trying to do and what are the goals we are trying to achieve. Then I will highlight some of the recent development in the electronic materials that's used for skin-inspired devices. And I'm happy to say that now we have a collection of materials that are very high performance with skin-like properties incorporated. And they now enable us to start building sensors and explore bioelectronic applications, which I will also highlight some of the recent development in those areas. So today's electronics are mostly made with silicon as the core material, silicon being rigid and brittle. As a result, the electronic devices that we use today are also rigid and brittle. If we look at the devices used for diagnosis and monitoring devices, they either do not provide sufficient information or they're very difficult to interface with the human body to allow everyday usage. Even for implantable devices, still very rigid components are being used today, and this severely limits the potential that modern electronics can be leveraged for health-related applications. So what we envision is a future where electronics are comfortable, invisible, imperceptible, biocompatible, and are able to collect health-related information autonomously. So to realize that goal, we have been pursuing the direction of we call electronic skin or skin-inspired electronics, where this large sheet contains sensors and signal processing circuits. And this large sensing sheet takes the form factor of human skin so that it can interface with human body intimately and do not cause any damage to the tissue or the surface it's in contact with. You may say that, well, for silicon, it can already integrate in high density and very small feature size sensing functionalities, signal conditioning circuits, and signal processing circuits and wireless communication circuits, all in a small form factor. And why do we still need skin-inspired electronics that, in terms of electronic performance, currently still cannot compete with that of single crystalline silicon? But the advantage for such a silicon device is its capability of high level of integration. So that means it can collect information in high resolution in a very concentrated region, meaning small region. But what we are interested in is human health. And human health is regulated by the communication between various electrical signal and biochemical signal throughout the body. And these signals are generated at the cellular level, which is on the order of a few micron to tens of micron. And these feature sizes are much larger than what the state-of-art silicon technology is able to realize. But on the other hand, the information is communicated through the entire organ or through the entire body. So the area coverage can be centimeters square to even meters square. So what we are really interested in is to be able to measure information at cellular level resolution, but over a very large area. And these are the potential areas where we think skin-inspired electronics can play a unique role. So what we need is, to begin with, materials that are as soft as jelly, but with electronic performance in terms of conductive material as good as metal, or semiconducting material as good as polysilicon or amorphous silicon. Single crystalline silicon might be difficult to realize, but at least amorphous silicon and the polysilicon. And they will allow us to be able to build a range of circuits. So my group has been working towards that goal over the past more than a decade. We have two areas of focus. One area is focusing on materials development, because they are the foundation for sensors and integrated circuits. And our latest circuit is the one shown here. And on the other hand, we also need sensing functionalities. So we started out with developing sensors that can mimic sense of touch, but now expanding to chemical sensors, electrophysiology sensors, and with the ultimate goal of electronic skin, which combines the sensors as well as the integrated circuits that we develop in the group as the long-term goal for the group. But along the way, there are many devices and many applications that the components that we develop can potentially enable. The key is the electronic material. And for any integrated circuits, the semiconducting material is the most basic element that we need to build transistors, which are used to build integrated circuits. And for the semiconducting material, charge carrier mobility is the parameter that's used to characterize the ability for the transistor to switch at a certain speed and to operate, to perform logic function. So in terms of materials available, on top listed are the various inorganic materials, and on the bottom are various organic materials and the polymers of different format. And through the fundamental studies by the community of organic electronics, the pink region, shaded region, represents the charge carrier mobility that's realizable with organic electronic materials. So you can see in terms of electronic performance, organic materials already are outperforming that of amorphous silicon and entering into the regime of polysilicon. But the key materials design challenge that we face is that now we want to incorporate skin-like properties into the electronic materials. But the traditional design concept for polymer semiconductors or polymer conductors is to design rigid conjugated structures so that it can facilitate the intrachain charge transport. And then the rigidity of the molecule also facilitate pi-pi stacking so that there can be good interchain charge transport. But this kind of molecular design results in brittle polymer thin films that forms cracks at less than 25% strain. On the other hand, for rubbery materials and elastic materials, the general molecular design is to have flexible polymer chains but this introduces a lot of conformation disorder and slows down the charge transport. So these two different requirements in molecular design to get both properties seem to conflict with each other. So our challenge is to figure out how we can come up with molecular design that address this seemingly conflicting requirements. So the molecular design studies we have been carrying out over the years have been trying to understand how we can balance the charge transport that requires rigid molecules, crystalline morphology with trying to get amorphous domains that will allow the mechanical property, but not having so much amorphous domains that the electronic property is being compromised. So we look at systematically the polymer backbone design to introduce disorder through various approaches, such as introducing the conjugation breakers to lower the rigidity, or using fully conjugated rigid species, but then making them more randomized so that then, even though they're fully conjugated, but having random comonomer units reduces the overall order. Also, we can tune the side chains to introduce disorders. So various these approaches have led to a number of promising designs that provided the minimum decrease in the charge transport level compared to the fully rigid structure and the crystalline structure. There's less than 20% decrease in the charge transport capability, while at the same time introducing the stretchability. On the other hand, we were also interested in looking for a more general approach. In polymer science, a common approach to achieve two functions is to have a blend. In this case, we need semiconducting property and the stretchability. So it's natural to think about having a blend that has semiconductor and a stretchable polymer. But the problem with the electronic polymer design is that this kind of design for electronic conduction will significantly degrade the conduction because the insulating material will take a fraction of the conductive components. And furthermore, the insulating material can get in between the conductive components and further reduce the charge transport. So it was very surprising when we first made this blend. We noticed that compared to pure 100% semiconducting polymer, even if with the addition of 70% of insulating polymer in the blend, we were able to see a doubling in the charge carrier mobility, which is completely unexpected. And then if we further control the coating conditions to control the fluid flow using this comb-like structure that we have previously been studying to control the flow pattern, we were able to further boost the charge carrier mobility of this kind of material so that the mobility now reaches, enters into the regime of that of polysilicon. And upon further investigation, we discovered that, in fact, with proper choice of the insulating polymer, here, we want to have them to match the surface energy of the semiconducting polymer so that there is no dramatic phase separation that will lead to isolated semiconducting regions. And then, on the other hand, we noticed that compared to the neat polymer, which the AFM shows a featureless structure, But with the addition of the insulating polymer, it results in these nano-confined nanofiber structure. And these structures were already formed in solution because in the solution UV-vis, we can observe the aggregation absorption peak increase in its intensity as we increase the amount of insulating polymer we add into solution. So basically, using additional advanced X-ray characterization, we determined that in this nano-confined structure, actually the polymer is forced to into more planar conformation and reduce the conformational disorder. And this is a key to result in much improved charge transport. And of course, the details of film formation is also important because these nano-confined structure need to be interconnected and they have to be in good contact with each other when the film is being formed. But with proper tuning, we are able to obtain such structure and with a boost in the charge transport instead of decreasing in the charge transport. And at the same time, we obtain the stretchability. So with these various molecular design approach, and especially the nano-confinement, we're able to significantly boost the charge transport of organic semiconductors to beyond that of the amorphous silicon level and entering into polysilicon regime. And we are very excited about this discovery of nano-confinement effect because it's a key for us to add other skin-like properties without degrading the electronic property and even enhancing it. For example, adding the biodegradability and the elasticity can be achieved by using a matrix that's biodegradable and elastic and a semiconductor that contains imine bond that can be readily hydrolyzed instead of carbon-carbon double bond. And for self-healable and stretchable polymer semiconductors, then we designed the suitable polymer semiconductor and its matrix so that it can also form the nanostructures that's needed. But in this case, having a dynamic polymer matrix allows these nanostructures to be carried across the damaged region. So originally, the semiconducting polymer itself is not dynamic, but the nanostructure embedded into the matrix is dynamic, and this leads to the healing of the semiconducting structure. And going from semiconducting material to conductive material, this nano-confinement effect again allowed us to incorporate multiple functionalities, such as high conductivity. This is a result of the nano-confined structure. And then addition of the stretchability as well as photo patterning capability. And this is realized by designing a single additive, which act as a cross-linker, photo-initiated cross-linker, but also it has the polar backbone of PEG backbone that's used to induce the nano-confined structure because this polar component can alter the interaction between the P dot and the stabilizing PSS and induce the nano-confined structure. But the PEG chain itself is crystalline. So just addition of PEG chain into P dot will result in a brittle film. That's why we had to thread the PEG chain through the cyclodextrin structure. And this allows the suppression of the crystallization of the PEG chain. And also, since these rotexine molecules can slide against the chain, so that provides mechanisms for dissipating mechanical strain. And then the side chains on these rotexin is with photo crosslink. Can be photo cross-linkable groups such as methacrylate terminals, and this gives us all the properties that are desirable. And this is the first stretchable polymer conductor that can reach conductivity that's at a level of indium tin oxide, and also being transparent at the same time. And even after washing with aqueous solution, it still remains to have a very high conductivity. And furthermore, the nano-confinement effect can be extended to light-emitting polymer. So here, the light-emitting layer consists of light-emitting polymer and a suitable matrix to induce the nano-confinement effect, but also stretchability at the same time. And this allowed us to have a stretchable all-polymer light-emitting diode with charge transport enhancement and high brightness all at the same time, and give us this new generation of stretchable light-emitting polymer and the light-emitting display that could be potentially interesting for interactive displays. So with this general concept of confinement, nano-confinement effect, and understanding of molecular design, then we can introduce photo patterning ability directly into the conductor and the semiconductor and the dielectric layer. So this can significantly reduce the number of steps it takes to produce these kinds of circuits. So instead of having to utilize photoresist, which can potentially also cause damage to the stretchable material, and we had only limited number of materials that would be compatible. And furthermore, with photoresist, we have to go through liftoff and or etching process, which adds a large number of steps. But use direct photo patterning to make these integrated circuits, we can significantly increase the density of the circuits as well as the yield for producing such devices, which is important to build more complex integrated circuits. So with such development, we were able to much increase the density of the transistors per centimeter square, as well as the charge carrier mobility. So for the first generation of stretchable integrated circuits, they were fabricated using photoresist and etching patterning, as well as combined with some shadow mask. So the transistor density was only 300 transistors per centimeter square, and the mobility was in the amorphous silicon range. Second generation, we were able to develop the materials to be directly photo patternable and still maintain the mobility of amorphous silicon, but much increase the charge, increase the density of transistors. Third generation that we're currently working on in the lab now realize much improved the charge carrier mobility as well as higher density. So these circuits, we believe now with such a fabrication capability will allow us to start building much more complex circuits to be integrated with the sensors. So basically, if one uses rigid components to build the sensor and the circuit integrated system with rigid components, then typically all the rigid components are combined together. The sensors may be stretchable and soft, may be in direct contact with the human body or with biological systems. And in this case, the sensors need to be relatively close to the rigid components so that the weak signal will not get lost through the traveling over relatively longer distance. And also the number of sensors that can be nearby is more in a smaller region, more integrated into a more densely packed region. But with the skin-inspired electronics and the capability of the circuits, we can imagine having the signal conditioning circuit moved close to right next to the sensor. And these are the parts that really need to be soft and skin-like. And this will allow signal amplification and digitization immediately after the sensing is performed. And this will allow the sensors to be spread over larger area and still be able to have high quality signals, and also can potentially reduce the size of the sensors or measure weaker signals because amplification is right next to the sensing front. So this would be the difference in the system level design. Or another way to look at it, with rigid integrated circuits, then sensors would be close to the rigid components. But with the soft components, then some of the circuit components are shifted to the sensing front. And this allows more distributed sensors at high resolution and also over large area. So next, I want to move to talk a little bit about highlight some of the sensor developments that we have been undertaking. So our first groups of sensors that we have been developing in the group involve physical sensors, physiological sensors, such as measuring the pressure and the shear force, compliance, softness, and temperature. Our first version of the sensor, the pyramid design, now has been adapted by many research groups to make sensitive force sensors. And this kind of sensors can also be incorporated into wireless, passive wireless sensing to reduce the size and form factor of the devices. And also they can be combined with more complex designs to mimic the skin sensing properties, so to detect shear force or strain force, or the combination of strain and the pressure sensor allows sensing of the compliance of the material. For example, differentiation of handling a soft strawberry versus a piece of glass. And then the circuit capability allows us to be able to design sensors that is only sensitive to, for example, temperature, and without being affected by strain or pressure. And here, a comparative circuit is used to generate the output of temperature. And this allows us to be able to take advantage of our capability for circuits and be able to make a more accurate sensor and a more selective sensor. For example, these sensors can be incorporated into wireless format. This is an example of passive wireless sensors that are used to measure pulse wave directly from the artery, or these sensors can be implanted inside the body. This is to show a example of wrapping the pressure sensor, wireless pressure sensor around a major artery. This allows us to detect potentially any blood clog inside the major artery, even tens of centimeters away from the sensor can be detected. A more recent example that we have explored using these sensors is to monitor the progression of tumor. And in this case, several string sensors are combined together. So here, these are cracked gold string sensors. And the combination of these sensors can allow us to detect the shape of the tumor when it changes size. So this application is of interest when there's a drug screening to screen the potential drug that's used for treatment of cancer. And such cancer cells can be injected into a type of mouse model so that this cancer cells will grow rapidly in the mouse model, and then different drug treatment can be tested to see, to know their effectiveness. And this kind of monitoring previously was done manually using a caliper like this one shown here to manually measure the change in the tumor size. Of course, this is labor intensive and cannot be done continuously, and it can also only be done with a limited number of animals. So previously it can provide feedback, but requires a lot of manpower. And also, when a certain drug is not effective, it requires extended time to be able to find out. And with the wireless device here, blue and red represent different kinds of treatment methods. And you can see within the first few hours can already be seen that the red type of treatment is the treatment represented by the red line is much more effective than the blue one. So this allows quick feedback for such a screening. And this is especially important for late-stage cancer patients where they are using immunotherapy. And if a certain therapy is not effective, then this can allow quick change to other more effective treatments. And then going from physiology measurement to electrophysiology, here the electrical signal is very important. That regulates many of the functions in our in the biological systems, and these signals range from those from the eye movement or to the brain information, to heart information, all the way to muscle information. And these signals can have a range of different frequency and also amplitude. But importantly, you can see even for the fastest signal, their frequency is in the order of kilohertz. So this range of speed is very accessible with the current skin-inspired electronics. And to measure these signals effectively, it's important that the electrode material has low impedance when in contact with tissue, and this impedance will impact how much signal can get across through the electrode into the electronics. And conducting polymer has been found previously to have a advantage over metallic materials such as gold or platinum, because its large surface area and also its ability to transport both ions and electrons gives it high capacitance at lower frequency. So both fact and combined with high electrical conductivity together can really significantly lower this interfacial impedance with the tissue. And this, the implication is that this can lead to smaller electrodes and still being able to measure high quality electrophysiology signal. Or for electrical stimulation, a lower voltage can be applied to still get high current injection for stimulation. And here we show the benefit of having small electrodes because of its low impedance for when it's localized stimulation. That's represented here using 50 micron electrode size. We stimulate selectively various regions of brainstem, which is the place where the spinal cord intersected with the brain, and it's a extremely sensitive region because there's constant movement of the neck movement that having a rigid device here may cause severe damage to the soft tissue. And here with our implanted high resolution electrode array, we can selectively stimulate the tongue movement or the whisker movement or the facial muscle. And you can see here the scale bar is a few hundred micron. So just hundreds of micron away would lead to control of a very different movement on the head of the animal. So that highlights the importance of having high resolution selective stimulation. And then for electrical recording, here to highlight the importance of high resolution, we show the muscle measurement with 100 micron electrodes that gives highly different dynamics that can be mapped with such electrode and provide details of single muscle fiber electrical signal. And to highlight the importance of having soft device, you can see from this histology slice of implanted electrode array. On the left is with the soft array. After a week or two, still the histology doesn't show any severe immune response or scar formation in this kind of device. But with even with the plastic substrate, even though it's flexible but has high modulus, much higher modulus than the soft devices, with even after implantation for 1 day, afterwards we see the histology already shows cutting of the device into the brain. At the same time, we observed the mouse tends to be paralyzed or have much reduced movement after such implantation due to the damage of the brain. This is another example of materials development, mainly the development of electrode material combined with the previous knowledge, but here in the gel, we incorporate into a thermally responsive material in here so that the electrode can be readily removed after the stimulation of continuous stimulation for scar reduce the scar for wound healing. And after the healing, just gentle healing allows the reduction of the adhesion and the readily removal of the pad. The last example I want to show is neurochemical sensing using the soft strain. Typically, these sensors are made with carbon fiber. If we don't want to use a genetic modification, and for human experiments, it's important to currently genetic modification is not allowed. But these carbon fibers are very rigid. So while it's possible to insert into the brain, it's not possible to perform such testing in a weak animal, especially in the intestine. And simultaneously, measurement of neurochemicals would both in the intestine and in the brain would provide new information that allows us to understand the regulation of such such neurochemicals and how that impact the brain gut axis. So here we developed these carbon-based sensors where there's the important part is having this precursor iron complex that was subsequently converted into iron oxide through laser writing. While the matrix is converted into graphene. And this is embedded into a soft stretchable substrate so that the neural strain itself becomes a soft and stretchable sensing strain. And this allows us to be able to effectively determine sense dopamine versus serotonin. Both are two important neurochemicals that's of interest. And then importantly, we are able to use this kind of probe to simultaneously determine the neurochemical in the brain and in the gut in the awake animal. So to summarize here, I've shown a few attributes of the current skin-inspired organic electronics for potential sensing applications. With the development of materials and circuits, this can allow high-resolution, large area mapping with tissue level softness, and a number of different kinds of sensing functionalities can be incorporated into these sensors. Finally, I would like to thank funding agencies, my research group members for their hard work and the creativity, and the many collaborators for their help to study various new directions utilizing our skin-inspired electronics. And thanks very much, and I'll be happy to answer any questions.
Thank you very much for the impressive and excellent talk, Professor Zhenan Bao. And we have several questions. And the first question, thank you for wonderful talk. The skin sensor is directly attached on the human body. In this regard, I'm wondering about the stability of various environments, humidity, temperature, air condition. Also, if we wear the clothes, how about the side effect of it?
Mm-hmm. Yeah, so the stability of the sensors depends on the type of sensors that we are looking at. For example, for pressure sensors and shear sensors, those force sensors, they are very stable because they can be constructed with well-known materials that are very stable. And then also those devices are not very sensitive to humidity. And for electrophysiology measurement, the sensors currently are actually exposed to moisture already. And in fact, having some moisture or even under liquid, it facilitates the ion transport. So for those kinds of sensing, also because the sensed signal is in terms of basically spikes. So the amplitude is not very important. It's more the spike patterns. So moisture doesn't affect as much. And finally, for the neurochemical sensors, we have implanted those sensors inside the animal for several weeks, for 16 weeks measurement, and we were delighted. And these sensors were coated with Nephium coating, and we were delighted to find that the sensed amplitude of the dopamine level was able to be maintained. But of course, for implantable devices, further studies will be needed to validate their long-term stability.
Thank you. Then we will take the one more question. Thank you for your interesting talk. I believe that the contact between skin or organ with your e-skin is possibly one of the important factors. Do you use any kind of binder, or how you improve the interfacial contact?
So depending on the situation, some cases we use another substrate that contains adhesive to attach our devices onto the skin. And in other cases, for example, for electrophysiology mapping, the electrode used for wound healing has adhesion as well as electrical conductivity, all designed into the material. So those kinds of materials are also available.
Okay, so I would like to thank the Professor Zhenan Bao again for the outstanding presentation. Thank you very much.
Thank you. Thank you.